Okay, so today we're going to talk about the ionosphere. So the ionosphere is basically the layer of the Earth's atmosphere that is composed of the ionized parts or composed of charged particles in the Earth's atmosphere, and this is embedded together with the neutral part of the ionosphere of the atmosphere. Okay, but before that, let us go over to what we've discussed so far last meeting. So last meeting we talked about the Earth's magnetic field. So at the first approximation, the Earth's magnetic field is a dipole field, and the magnetic dipole has several components in the uh, local coordinate system. So locally, the magnetic field of the Earth, especially in the surface, is described in terms of its horizontal and vertical components, where the vertical component is directed downward to the ground. The X and Y components, or the horizontal components, are pointing towards the geographic north and the geographic east. And then the magnetic field line will generally point along the direction where your magnetic north is situated. So the angle between this direction, the direction of H to the geographic north, would be your declination. The angle between the horizontal component H to the direction of the magnetic field is called the inclination or the deep angle. Okay. And these components are related by these equations. Okay. So if you're going to graph those values using, let's say, the World Magnetic Model of 2020, the magnetic intensity or the total intensity in nanotesla on the Earth's surface is given by this contour graph, wherein higher or the redder regions implies that the magnetic field intensity there are larger than those in the blue areas. So the total intensity, therefore, around our area right now, based on this model, is about 41,000 microtesla, or 41,000 nanotesla, or 41 microtesla. This is way larger than the magnetic field carried by the solar wind. Because remember, in our previous discussion, the solar wind intensity or the interplanetary magnetic field has a magnetic field magnitude of the order 5 to 10 nanotesla. Okay, so around three orders times more than the magnetic field of the Earth. Now, what's more important in this graph is also the presence of what we call the South Atlantic anomaly, wherein this is uh, a irregular depression in terms of intensity in the South Atlantic. So what's important with this region is that the protection provided by the Earth's magnetic field is least in this area compared to the other areas. Okay, so aside from the total intensity, the magnetic field can also be expressed in terms of its horizontal intensity, wherein we expect that the horizontal intensity along the equatorial region would be the greatest, because most of the magnetic field there has a horizontal component with uh, very minimal vertical component. So the horizontal component is about 39,300 nanotesla using this model on the Earth's surface. Okay, and the vertical component, on the other hand, is very minimal in the equator. So the locations where there is zero vertical components is what we call the geomagnetic equator. And based on this model, the geomagnetic equator is in the Philippines is around the region where Mindanao is located, um, which is about a few degrees higher than the geographic equator. So this zero is actually the geographic equator. The line are what we call the zero line is what we call the geomagnetic equator. And this is very important, especially if we're going to describe how magnetic field uh, dictates or contributes to the behavior of the ionosphere. Okay, so aside from the vertical component of the magnetic field, we can also use the inclination angle or the dip angle to locate the direction of the or the location of your magnetic equator. So if this is your magnetic equator expressed in terms of the vertical component Z of your magnetic field, that line will coincide to the magnetic equator. Okay, so magnetic field, the inclination or the dip angle in our area is about 17 degrees. Okay, so declination on the other hand is the angle between the direction of the magnetic field line in the horizontal direction and the direction where you're pointing at the geographic north. So here in the Philippines, the declination is negative 2.3 degrees. So that means if you use your compass to locate the north direction, the geographic north, your compass reading will be about 2.3 degrees off. Okay, so that's the definition of your declination. Now, this magnetic field interacts with the magnetic field provided by the solar wind. So when the solar wind interacts with magnetized objects, it basically forms the Earth's or the planet's magnetosphere. Okay, so these are some of the models provided by these researchers. And this tells us that the magnetosphere, so this is the region where the magnetic field of the Earth is very significant relative to the interplanetary magnetic field. Okay, so the magnetosphere has these parts, and you already have your homework related to this, wherein I ask you to mention or state the plasma density as well as plasma temperature of these regions of your magnetosphere. So you have your magnetosheets, polar cusps, magnetopause, the bow shock, the plasma sheets, neutral sheets, and the magnetotail lobes, and your plasma mantle. So these different regions are basically defined by their plasma temperature and their plasma density. Okay, so and aside from the magnetic field configuration, because this magnetic field, the magnetosphere is actually composed of plasma, and because you have interaction with the magnetic field, therefore these particles will eventually drift. Okay, so one of the drifts that we talked about is the curvature drift. You also have your E cross B drift, etc., etc. So those drift velocities, so those drift made by the plasma trapped within the magnetosphere are the most responsible for the formation of your current systems. So these are the major current systems that are present in the magnetic field of the Earth or the magnetosphere. So you have your ring currents, you have your magnetopause currents, you have your field aligned currents. So the field aligned current is basically the current presence where when charged particle is actually funneled through the polar cups. Of course, you have your neutral sheet currents and your tail currents. Okay, so the ring current and magnetopause current are two of the current systems in the magnetosphere that affect the equatorial region of your magnetosphere. And how important is that? Because the Philippines is in the equatorial region or low latitude region. So any changes that happens in the green current and the magnetopause currents brought about by influences, let's say solar wind influences, will have an effect to the local surface magnetic field, which will have an effect in the behavior of the ionosphere and other space weather effects. So that's why I focus more on these two current systems last meeting. So one of the influences or one of the effects, if there are changes in the ring current and the magnetopause current, as solar wind becomes disturbed or brings transient energy like CMEs or high fast moving solar winds, one of the effects is that presence of geomagnetic storms. So this is an example of a geomagnetic storm that happened in September, caused by solar flares or X-class solar flares last September 2017. Okay, so using the DST index and the KP index, we can actually characterize these days or these days from September 4 to 12 by in terms of two main or two distinct conditions. So you can call a day as a quiet condition, and you can also call a day that is in disturbed condition. So we use DST index and KP index to quantify how disturbed our geomagnetic field is, especially near the Earth's surface, which may affect several of our technologies. So one of the effects of such geomagnetic indices is that the total electron content that is present in the ionosphere may vary, okay, or may have some anomalies, or may be enhanced, or may introduce some depletions in the Earth's total electron contents. So this is an example of measured data in the Philippines, where during this disturbed period, you can see there are there is an enhancement in the total electron content compared to the days wherein the Earth's magnetic field is generally quiet. Okay, so with that, let me start discussing the Earth's ionosphere. So the Earth's ionosphere, as I mentioned before, is the layer of the Earth's atmosphere wherein presence of charged particle, positive ions and negatively charged particle, ions and electrons are dominants. And this is embedded in the Earth's neutral atmosphere. So if we're going to compare the Earth's ionosphere generally has four regions. You have your D, E, F1, and F2. And these are characterized based on the Earth's electron density. Okay, so based on the Earth's the atmosphere's electron density, we can classify the layers of the ionosphere based on this. Now, comparing this to the neutral atmosphere, wherein the neutral atmosphere is defined by the temperature gradient. Okay, so based on the temperature changes, we can define the following layers of the atmosphere. So you have your troposphere, described by a decreasing change in neutral gas temperature. And then next layer would be your stratosphere, characterized by your increase in temperature of neutral gas, and then another decrease. This is your mesosphere, and then you have your thermosphere. So you notice here that most of the ionosphere are located within the region of your mesosphere and your thermosphere. So within this region, you can actually see your air glow, which you're going to mention later. You already mentioned about the aurora. You actually have a homework about this. And then your satellites are actually, most of your low Earth orbit satellites are actually located in the thermosphere or the ionosphere. Have your sounding rockets, etc. Okay, so how one important thing to remember when we talk about the ionosphere is that the ionosphere uh, is uh, is formed if the Earth has two things. Of course, you should have uh, source of that ionization, energy source. So in our case, we have your sun. So the sun is actually the one that provides the energy to ionize the atmosphere. And then what should do we ionize? You should have a neutral atmosphere. It, if the if the planet, for example, has a thin neutral atmosphere, naturally it has a very thin ionosphere because the source of charged particle that you can find in the ionosphere are mostly come from uh, the neutral atmosphere ionized by the sun. So different sources of ionizing energy can be found from the sun. So you can have X-ray, extreme UV, far ultraviolet, visible light rays. Infrared doesn't provide any ionization energy. Okay, so only the ultraviolet to X-ray. Those are the wavelengths that basically ionize the Earth's atmosphere. Okay, so to give you an overview how the ionosphere is formed, uh, to make things simpler, the formation of ionosphere basically um, follows the continuity equation. Okay, so you're already familiar with the idea of continuity equation. This is basically a balance equation wherein the formation of such constituents is equal to the processes that provides that or that makes that 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 parameter or that constituent. So for example, in the ionosphere, this is described in terms of formation of charged particle. Okay, so the continuity equation basically reflects the effects of various processes that form your plasma concentration or your former plasma. So the rate of ion concentration or the rate of change of your ion concentration is equal to is related to these three processes. Of course, you have your gain in terms of production. So this term describes how charged particles are formed. Of course, there is also some form of destruction. And then at a certain locality, particle ion concentration can also change by by Newtonian motion. Okay, so for example, the Earth's ionosphere or the ionization in the polar caps changes when there is precipitation coming from the sun through the solar wind. So that's an example of your precipitation, okay, or change due to transport. There are a lot of processes that that can be attributed to this process. You change due to transport. Okay, so but basically, in terms of in equation form, the rate of change of ion concentration, derivative of Ni. Ni is the ion concentration with respect to time is equal to the production or Qi of that specific ion species minus loss minus motion. Okay, so this is the motion, and then you have your divergence. So if your divergence is positive, so that means you have a source. So that means negative divergence means you're going outward. So in a certain locality, the particle, the concentration of ions is decreased. If this term is positive, therefore there is an introduction of additional charged particle. Okay, that is caused by motion of those charged particles. Okay, so main source of production would be your photoionization. As I mentioned earlier, the electromagnetic radiation is on the form of in extreme UV and X-ray are the main sources of this energy. Of course, there are other sources of energy too that can ionize particles in the atmosphere. Let's say, for example, cosmic rays and other sources of energy. On the other hand, the main source of loss of charged particles would be recombination. So that means your charged particles, let's say positive ions and negatively charged particles like, let's say, electrons, recombine due to Coulombic forces. So when they recombine, the amount of ions present in the ionosphere changes, and this process is uh, is is dominant during nighttime, of course, because during nighttime, the source of your ionization, which is the sun, is not present in that specific locality. But photoionization is the main source of production, and the ionization, of course, happens during daytime. Okay, so the amount of ions or the ion concentration present in the ionosphere has a diurnal variation. Of course, the day side will have more ionization than the night side. Okay, so let's focus on right now. So let's focus on photoionization. So the ionospheric layers are formed by photoionization of ions or atoms, neutral atoms, and some molecules. Okay, so mainly we owe the ionization from the extreme UV radiation from the sun. Okay, so that's why if there are, for example, solar flares, which are, as discussed before, now when you have solar flares, those are sudden brightening of the sun's extreme UV and X-ray. So if when that happens, the ionization formed through photoionization, or the ions formed through photoionization, would generally increase. Okay, so the chemical equation that is usually found, or that usually follows this process, is this one. No? So when you have your H nu, so this is your energy coming from the sun, is ionizes your atom. That atom will eject a free electron, and then the original atom will become positively ionized. So that's why the ionosphere is actually quasi-neutral, just like any plasma regions or any plasma form. Okay, so usually we describe the ionosphere that's in terms of the electron density more than the ion density. Okay, because whatever the form of the ionosphere described by the electron density, more or less that's the same form that would be followed by your positively charged particles. Okay, so in terms of, for example, molecules, the same thing happens. Your EUV radiation will ionize your molecule, and then that molecule becomes positively charged particle plus a release of electrons. On the other hand, recombination happens when the photoionization source, or the energy that causes photoionization, becomes absent. So these two, the formerly separated free electron and positive ion, therefore naturally recombines. Okay, so in this case, the process is generally a reverse. So your positive ion recombines with an electron, and that would create your neutral atom plus a release of energy. This is usually of the form of light. And this light is one of the mechanisms that form your air globe. So this is a slow process. For molecules, a bit fast. No? If a positive ion combines with a positive ion molecule or positively charged molecule, recombines with an electron, what can happen is that you, these two constituents of the molecule can be separated. So we call this process, a fast process, we call this a dissociative recombination. This leads to the splitting of this molecule into two atoms in an excited state. So this process is effective because impulse and energy can be distributed among these two products. So therefore, this process will not produce or will not release photons. Okay, just to give you an idea, what is this air glow? No, I think you can already see this in pictures over the internet. Okay, so if you see this picture, this bright picture, this bright layer, okay, several kilometers from the Earth's surface, this is not aurora. Okay, so this is what we call your air glow. Okay, aurora is different, but they basically form along the same region. But the mechanism of the formation of air glow is different from the mechanism that forms your aurora. So if you're going to see this picture, usually you can see this picture, and what is being featured is the aurora and not the air glow. Okay, so I hope that when you see something like this in the future, and not only you will appreciate the beauty of this aurora, but also you also appreciate the air glow. So air glow is always there because recombination always happened. But again, as I mentioned earlier, recombination is only one of the processes that produces air glow. Okay. So these are some of the examples of chemical processes that happens in the ionosphere. So for photoionization, your oxygen at your atomic oxygen, your molecular nitrogen and oxygen actually forms this O plus and N2 plus and N2 plus ions plus electron. So this is your typical photoionization. Okay, next would be your rearrangement collision. So what happened here is that aside from photoionization, as a fraction of the ionized charge ions or ions in the ionosphere can also form using or through rearrangement collision. So for example, this O plus ion collides with N2 plus, like this one. So when they combine, what happens is that this ion or this molecule, N2 molecule, would split. So one of the N2 atoms in the N2 molecule will attach to the O plus, forming NO2 plus, and then you have the another product would be your atomic nitrogen. So same thing goes here. So for example, sorry, this should be O2 if I'm not mistaken. Yeah, this should be O2. Sorry about that. So O plus plus O2 equals O2 plus plus atomic molecule, atomic oxygen. And then N2 plus O can form NO plus plus nitrogen. So similar to this one. So this is a schematic drawing of that. So this is happening due to collision. So this is energy transfer due to motion. Of course, you also have ion loss by dissociative recombination. So when this positively charged ions recombine with free electrons, you form these atomic molecules, okay, which I already mentioned to you earlier. Okay, so these are other processes. So free electrons can actually attach, okay, to some extent, to attach to molecules. So when they attach, that molecule will have an excess electron, therefore become a negatively charged molecule. And then this negatively charged ions can also be lost by photodetachments. So for example, if a negatively charged ion like this one is hit by an ionization energy, that excess electron can be ejected from itself, therefore going back to its original neutral form and then freeing that extra electron. Okay, so as you will notice that, as I mentioned earlier, that electrons is the one that is used to characterize the layers of the ionosphere. Okay, so now formation of the ionosphere has a dependence on altitude or height from the surface. And there are two considerations that needs to be done. Of course, you have to know how density of your neutral atoms changes over heights. Okay, so we know that as you go up, the density of your neutral atmosphere generally decreases as height increases exponentially. Okay, so that means there are fewer neutral atoms or neutral gases found in the upper atmosphere than in the lower atmosphere. Okay, so and then of course, as I mentioned earlier, if you want to form an ionosphere, not only do you need neutral atoms and molecules, you also need source of ionization. So because the source of ionization of the ionosphere is mostly coming from the sun, so that means you have to know how electromagnetic radiation coming from the sun changes as a function of height. Because we know that these charged particles, neutral particles are absorbed by this. Because these neutral atoms or neutral gases absorb energy coming from the sun. So that means the energy as a function of height would have some sort of a decreasing behavior. So that means at the upper atmosphere, you can actually receive more ionization than the lower atmosphere. Okay, so the solar flux can be described as a function of this. Okay, so a combination of a decreasing density and an increasing radiation. So the combination of these two will actually be followed by your ionization rate. So what does it mean? It means that while above you have more ionization, you have more energy to ionize particles, you have fewer particles, or you have fewer constituent to ionize. So that's why the ionization at the upper atmosphere is low. On the other hand, if you go further below, while you have a lot of gases that can be ionized, but at that height, only the energy that is required to ionize these gases is very low in energy. So that means the ionization there will also be low. Okay, so that means we will expect that there is some kind of a peak height. So this height would basically describe that at this height, the amount of the density of your charge, the density of your neutral particles, and the amount of ionization energy is optimum. Okay, so this is what we could expect from an ionization. That's why when you saw earlier the graph, we have a shape like this, and we're going to talk about the shape a little bit later. Okay, so let's say you have your EUV radiation. So this EUV radiation, as I mentioned earlier, is the main source of ionization in the ionosphere. Okay. And then we can actually quantify this by considering this set of derivation. Okay. So from this slide, what I'm going to describe is how this ionization layer is actually formed for monochromatic energy. So that means single wavelength or single frequency energy, and then single constituent. Okay. So this is just a simplification of the process. So let's start. So the ionization rates, QI, for the ith ion species at altitude H, okay, is given by this, no? Of course, you have your ionization rate would be equal to the radiation intensity times the density, of course, times the cross-section, ionization cross-section. Okay, so what does it mean? So that's the product between the amount of energy that is used for ionization, the density of the particulate or constituent ion that is ionized, plus how effective, okay, how effective the ionization happens. So that's what we call the ionization cross section. Okay, so in equation form, that's equal to phi QI equals phi Ni phi II. So Ni is the neutral particle density at altitude H. Phi is the EUV flux, and then the ionization cross section is sigma II. Okay, so this is sigma II. Okay, now because the energy flux varies with wavelengths, and then the ionization cross section also varies with wavelength. So that means this ionization cross section, the effectiveness of this neutral particle to be ionized by this radiation will also depend on the wavelengths of the radiation. Okay, because remember that wavelength and frequency of photons is will dictate the energy of that photon or radiation. Okay, so therefore, the ionization rate for this specific species, let's say oxygen, atomic oxygen, molecular nitrogen, or let's say molecular oxygen, it can be the sum of these things. Okay, so this sum is for all wavelengths that is present during ionization. Okay, but we can simplify this calculation by focusing on individual wavelengths. Okay, so that's why we call it, that's why we will consider in the coming slides monochromatic ionization. So ionization at specific wavelengths only. To simplify this, the calculations. Okay. So one important thing that we should be familiarized with is the concept of optical depth. When you say optical depth, as the name suggests, this is the depth of, this is the depth or thickness. Sometimes we call this optical thickness. So how thick a material is optically. Okay, so this is related to how well a certain, let's say a certain material or gas effectively absorbs energy. Okay, so at different wavelengths, the same gas particles can absorb or scatter light differently for different wavelengths. So in terms of the solar flux, reaching at this altitude H, the flux is given by this equation. P infinity is the solar flux outside the atmosphere. Okay, and then the amount of solar flux reaching, penetrating the atmosphere actually changes exponentially. And the amount of decrease depends on the optical depth. Okay. So the optical depth is theta, is tau, and that is dependent on the wavelength. So as I mentioned earlier, same material can have different optical depths depending on the color, so to speak, or the frequency of the lights. Okay, so for example, water vapor has a high optical depth in infrared than visible wavelengths. Ozone has a high optical depth in UV than in visible because it absorbs more UV than other wavelengths. So that's the idea of optical depth. So that means optical depth is a function of the following. It's a function of where scale heights, where the particle is, because remember that the height will also dictate how much energy is being absorbed already or has been absorbed already, and would be the density. So how many of that specific gas molecule is present. Of course, the more gases present, the higher the optical depth because more of these constituent particles will absorb this energy. And of course, the cross-section or absorption cross-section. So this tells us how effective that certain molecule absorbs that specific wavelength. And of course, the angle at which the zenith angle, okay, so this zenith angle is the angle, is the angle of the ray path coming from the sun to the surface. Of course, if the sun is directed above, that means the energy that is absorbed by this molecule is concentrated to itself. Unlike if it is, let's say, in the sunset, during sunset or during sunrise. Okay. So this is your optical depth. So what's important thing to notice here is that yung optical depth is a function of this zenith angle. Okay. Yeah, so this zenith angle. Okay. Now, so therefore, if we're going to put this equation in this equation, okay, plus several additional plus this equation, okay, the ionization rate at a certain wavelength for a specific ion species would be given by this equation. Okay, so what's important to notice here is this, that the ionization rates for a specific species of neutral gas that is ionized by a specific wavelength of light depends on two things. It depends on the zenith angle chi and the height. Okay, so the upper limit of altitude and atmospheric density diminishes and the ionization rate decreases. So the lower limit, on the other hand, ionization rate also decreases because of the weakened EUV flux. So here, due to the absorption of most of the ion, most of the material, most of the atmosphere on top. Okay, so there's what we call a altitude where ionization rates is maximum. Okay, so that's the idea. So this ionization rate would depend on the uh, zenith angle of the sun. So that means it will depend on the time of the day as well as the heights, because this height will determine the amount of density for a specific frequency, for a specific species. Okay, so where is this height? So if this is your ionization rate, so what we can do is to find this, we just differentiate this function. So function of heights. And then we set the zenith angle to be 0 for maximum ionization rates, because the sun would be directed overhead if zenith angle is 0. Because if zenith angle 0, therefore the secant function chi, a secant of chi or secant of 0 would be 1. Okay, so if we're going to differentiate this, therefore the altitude where q is maximum is given by this equation. Okay, so normalizing this heights with hm with the scale height, we're going with this. So that means if z0, the height is where you can find the maximum height. Okay, this will make more sense if you're going to show this in a graph. But anyway, so substituting this equation here will and then normalizing it with maximum ionization rate will be given with this equation. So this function e to the 1 minus z minus secant chi e to the negative z, this is what we call the Chapman function. So this Chapman function basically describes the shape. Okay, not the absolute value, but the shape of your layer, of your ionization layer. As I mentioned earlier, this will depend on the zenith angle as well as the heights. Okay, so if we're going to graph this function at different, let's say at chi equal to 0, so that means the sun is at the zenith direction, and then at 60 degrees zenith angle, and then let's say towards the sunset with, let's say, 87 degrees, you'll end up with this graph. Okay, so the solid line is for the zenith angle equal to 0. The dotted line is for 60 degrees, and then dashed line is for 87 degrees. Z0, as I mentioned earlier, is where you can actually locate your maximum ionization that can be formed. Okay, so at different zenith angles chi, you can actually identify the ionization peaks. So as you go lower, as the sun goes lower or near the horizon, meaning you have higher zenith angle, the amount of peak ionization decreases, and the height where you can find that ionization increases. Okay, so that's the basic behavior of a Chapman layer. Of course, you can actually express this in logarithmic scale in the x-axis. So if you're going to look at the logarithmic scale, it would look like this. Okay, and this is the one that is more familiar to us. So this shape is actually would basically follow this shape. Can you see the? Can you match the shape? So this shape is actually the shape. Of course, the true ionosphere has different layers because number one, at different heights, the constituent gases are different. You already know that. Of course, the sun will also provide different wavelengths of ionization energy. So this will complicates the shape, thus giving a form of different layers. But the general shape would be this one. Okay, so this shape is for logarithmic scale. So this is a logarithmic scale. This is actually a logarithmic scale. So this Chapman layer, as I mentioned before, only pertains to single species at single wavelengths. And if you add additional species, if you add additional wavelengths, this Chapman layer would be a superposition of those combinations, thus we expect that if we're going to model the ionosphere, Chapman layer is one of the mostly used models to model the ionosphere. Okay, so from here we can actually define the layers of the ionosphere. Okay, so this is your electron density, which is directly proportional to your ionization rates. This is height. Again, as I mentioned earlier, this scale is logarithmic scale. Okay. Now, different layers of the ionosphere is due to different dominant sources of ionization. The F region, the highest layer, is formed mostly by extreme UV, 10 to 100 nanometers of energy. Soft X-ray and far UV are the dominant source of the formation of the ions in the E region. And then the hydrogen Lyman series, alpha, which is different from the Balmer series. So this is UV. Balmer series is visible. Paschen series is your infrared. So the UV emission spectrum, specific at 121.6 nanometer, is the main wavelengths responsible in the formation of the D layer. And to some extent, that very, very minor layer, the C layer. Okay. So from this figure, if you're going to see this figure, two ionospheric parameters can be determined. Okay. One pertains to the density and one pertains to the height where that density happens. So we call that density the NMF2. So NMF2 means you have your density N, M means maximum, F2 means the layer. So this is the maximum density of the F2 layer. So if we're going to read papers about ionosphere, some papers describe the ionosphere in terms of the NMF2 or the maximum density at the F2 layer. And this happens at the HMF2. HMF2 is the height in the F2 layer where maximum ionization happens. This is very important to know the NMF2 because most of the ionization happens in the F2 layer, especially in the daytime. Okay? So, because these ionospheric layers are very far up relative to the surface of the Earth, so that means there will be times that the night side of the Earth will have a decrease in ionization way past local sunset. Okay, so what do we mean by that? So if we're going to illustrate that, so if this is your Earth, this is your layers of the ionosphere. So you have your D, E, F1, and F2. So D, E, F1, and F2 are actually formed on the day side. But on the night side, due to the recombination, which I'm going to talk about later, the F1 and F2 combine to F layer, and then E layer is weakened because there's not much ionization energy present, and then the D layer vanishes. So if we're going to look at this graph is your nighttime, this graph is your daytime. So during daytime, you have your C, D, E, F1, and F2 layer. But on the nighttime, you only have F region, which is a combined version of the F1 and F2 region, or the combined F1 and F2 during the daytime. And then you have your weaker E. Then the density in the D layer and C layer, if there's a C layer, completely vanishes. Okay. And then as I mentioned earlier, even way after sunsets, okay, because at the higher levels, the sun is still shining that layer of the atmosphere, ionization still take place. Okay, so that means this kind of this reduced ionization happens at a very at a shorter time period or shorter period during the day. Okay, this is about a few hours only, not 12 hours. If we're going to expect that now. Okay, so let's look at these layers individually. F2 region. This is at heights at a given altitude, the chemical process in the production. Okay, at heights below a given altitude, the chemical processes in the production and loss are dominant, wherein electron densities continue to increase with increasing altitude and in accordance to photochemical equilibrium profile. However, the altitude continued to increase, photochemical processes eventually decrease or becoming significant. That's why on the top layer, called at the top side, the ionization rates decreases. Okay, after reaching that peak ionization. And then during nighttime, when ion formation is absent due to the absence of energy source, the density rapidly, the electron density or the ion density decreases, especially in the lower part, because of losses in the ion concentration due to recombination. Okay, but plasma is supplied from the top side because there are a lot of ions at the top side by ambipolar diffusion. Okay, so this ambipolar diffusion is the process that maintains this density, electron density, during the nighttime. Okay, so again, during the nighttime, because photoionization process is absent, the ambipolar diffusion will become dominant. Okay, thus preserving some of the ionization during nighttime. Okay, so the form of the layer is preserved, but again, the density would be decreased, just like this one. So this form is maintained. Okay, so this Chapman layer is maintained, but the density is reduced. Okay, so this layer exists from about 220 to 800 kilometers. Atomic oxygen provides the O+ atomic ions that make up this layer. Okay, approximately around 300 kilometers to 400 kilometers, where you can find the maximum electron density in the F2 layer. Okay, so during daytime, an F1 layer is located about 150 to 220 kilometers above the surface of the Earth. Okay, and during nighttime, as I mentioned earlier, F1 and F2 merge into one F layer. Mostly it is composed of O2 plus and NO plus molecules with molecular ions and O plus ions. Okay, and mostly it appears during daytime, and most of the time it is present during the summer and solar minimum. So you will notice here that the dependence of your ionosphere in terms of temporal variations as well as solar activity variations. E region is roughly around 90 to 150 kilometers above the ground. This is the first one, actually, this is the first layer of the ionosphere that was detected or that was discovered. This is predicted by Edwin Kennelly and Heaviside. That's why sometimes we call this layer the Kennelly Heaviside layer. Okay, and after this prediction, a British scientist named Edward Appleton, okay, was able to prove the existence by allowing radio waves to be reflected off that E layer. That's why it's called E layer. It's called E layer because it's E stands for electrified. So when Edward Appleton transmitted signal towards the atmosphere, it was reflected. So what they say is that this is the electrified region in the Earth's atmosphere. That's why it's called E layer. And then D layer was discovered less because it was named D because it's before E. And then F was discovered later, and that is named F after E. So that's an alphabetical order. Okay, and in fact, this is the, if I'm not mistaken, this is the uh, first and only Nobel Prize winner in physics that is related to space weather and radio wave propagation. Okay, in 1947. Okay, now D region is found at about 860 kilometers to 90 kilometers above the Earth's surface. It is dominated by the NO plus and O2 plus ions, and it tends to increase during winter, but because of the lower zenith angles. Because remember, when you have lower zenith angles, so that means you have the ionization energy is actually penetrating lower in the Earth's atmosphere. Okay, it completely disappears during nighttime, where recombination process is dominant because of the absence of ionization. Okay. Now, another parameter that we use to describe the ionosphere is that if we have this electron density, we can actually calculate the total electron content. So if this is your electron density profile, you can actually integrate this profile to come up with your electron density, to come up with your total electron content. Okay, so the integration happens from the bottom of the ionosphere to the top of the ionosphere. So if this is your layer of the ionosphere, and let's say you have a column of your ionosphere in this way, so the total electron content is just a sum of the electron density from the bottom layer to the top layer. So this is your total electron content along this column. And if the total electron content is integrated in a vertical manner like this, we call that your vertical total electron content. So sometimes we call this TEC as slant total electron content, or STEC, just to distinguish this from your vertical total electron contents. Okay, so far we've used we've talked about three parameters to describe to describe the ionosphere. We have your NMF2, so that's the maximum density in the F2 layer, and then HMF2 is the height at which that peak ionization is found. And then if you integrate the electron density, you can define the total electron content. And personally, my research in space weather mostly revolve around the measurement of total electron content. Okay, so okay, so from this graph, aside from the fact that we can actually identify the different layers of the ionosphere, D, E, F1, and F2, or E and F during nighttime, you can actually see that there is several variations now. This figure shows that the ionization or the ionosphere, the ionization in the ionosphere varies with the time of the day. Of course, during daytime, we have high ionization rate because of the presence of the sun, presence of sunlight, and then during nighttime, it is decreased. Since most of ionization happens through photoionization, so that means any climatological changes in the sun's output energy will also have an effect on the ionization. So we already know before that solar cycle is an 11-year cycle, and it follows the 11-year variation of the magnetic activity, solar flux, etc. So that means higher solar activity, it will provide higher ionization than during solar minimum. Okay, and then the zenith angle of the sun will also have an effect on the ionization, as I mentioned earlier. So that means different regions of the Earth, because of the curvature, because the Earth is round, different locations or different latitudes on the Earth will receive sunlight at different solar zeniths. So that will also have an effect to the overall ionization. So as you will notice, the study of the ionosphere is very complicated. So let's look at those, let's visit those variations in a little bit more detail. And I plan to do this for the next 15 minutes now. So one of the variation that we can actually study with the ionospheres is spatial variations. So this is an example of a graph that shows a spatial variation. See, spatial variation, you can see the ionization that is the ionization in the ionosphere varies with heights. That's the first basic one. Higher heights means higher ionization up to the peak layer, and then after the peak layer, the ionization decreases. Location is also very important, as well as the, so for example, this one on this graph. Okay, so this follows the ionization. So this region, okay, where you can see red and light blue and green, this is where you have high ionization. So this is, so that means this is where the side of the Earth is facing the sun. Okay, so this is your density at the F2 layer. And then naturally, because you have more ionization, that means you have higher heights. So at this region where you have high ionization, that height of that F2 peak layer will also be higher, around 400 kilometers. But regions where there is low ionization, that peak layer is actually at lower altitudes. Okay, that's your geographic or spatial variations. And what you can also notice here, that's that you have two peak layers here. You have two peak layers here, one and one. So you have two peak layers. And if you're going to look at the cross section, altitude versus latitude, you can actually see that peak more detail. So there's a north and southern crests. So we call this the equatorial ionization anomaly. And this is one of the applications of your E cross B drift. In the magnetic equator, there's a presence of an eastward electric field. I am not going to discuss this, where does this eastward electric field came from, but for now, let's just say that there's a presence of, let's just accept first for now, the presence of an eastward electric field. So if the eastward electric field is pointing to your screen, therefore to your left is the north side, and the south side would be on this side. Okay, so we already mentioned the magnetic equator is where the magnetic field is horizontal. So if you have an eastward electric field and if you have a northward magnetic field, again, if you have an eastward electric field and if you have a northward magnetic field, E cross B drift says that any ionization that is present above the magnetic equator will drift upward. Okay, it will drift upward. And then because of gravity, pressure gradient along the magnetic field line, this the ionization that will drift upward will move sideward. Okay, thus forming this ionization crests. We call this the fountain effect. Okay, so there is a upward drift at the magnetic equator, and it will fall, and this will follow the direction of the magnetic field toward north and toward south. So that's why we have two crests here. Okay, and this is always present in the Earth's ionosphere. Okay, so aside from this, we can actually notice the temporal variations of the Earth's ionosphere. Okay, so the x-axis here would be the NMF, the local time. Okay, local time. And then the left panel is your NMF2, right panel, HMF2. Okay, So from here, you can notice, you can notice here that during daytime, this is daytime, the ionization actually increases. And then during nighttime, this is midnight, during this is 6 a.m. local time, the ionization is very low. So there's a diurnal variation in the MMF2 and even in the HMF2. But surprisingly, the HMF2 decreases, the ionosphere is lower during daytime and it is high during nighttime. Okay. Now, aside from this, you can actually also see this figure, okay, some form of temporal variations. So this is in Mohe, China, Beijing, China, Wuhan, and Sanya. So if we're going to look at the locations of this data, this is Mohe, Beijing, Wuhan, and Sanya. Okay, so you will notice here that as you go toward the toward south from Mohe, the amount of ionization increases over time. Increases as you go near the equator, similar to this one. Okay, so that's your temporal and spatial variation. This is also observed in India. So this first row is vertical, is in Trivandrum, 8 degrees north. Voltaire is 17 degrees north. And then New Delhi is 28 degrees north. So going down a row top to bottom, you go further north. Okay. So, and then this is, of course, you can see the diurnal variation of the vertical TEC and your NMF2. So they follow the same trend as this. During daytime, it is a higher, there are higher ionization. During nighttime, you have lower ionization. Aside from that, the diurnal variation, you can also see your seasonal variation. Okay, so you during winter and summer equinox, winter solstice and summer solstice, the general trend is that ionization during solstices is lower than ionization during equinoxes. And that is because of the zenith angle dependence on the Chapman layer. Okay. And then also, as you go further north, ionization or TEC and MF2 decreases, just like this one. You go north here, ionization decreases. You go north downward, ionization decreases as well. Okay. This is another sample of a temporal variation. This time, this is a global TEC map. Okay, so what's important to notice here is that while the rotation of the Earth follows the direction of follows the rotational axis, but the region where you have high ionization due to solar radiation is actually followed by the magnetic configuration. So you're already familiar with this magnetic field configuration. So wherein this central white line is your magnetic equator, and then the upper and lower lines are your plus 20 and minus 20 degrees magnetic latitude. So you will notice here that the magnetic field, the ionization follows the magnetic field lines. So this is moving because the Earth is rotating. So wherever this ionization is found, this region of ionization, that is the region of the Earth facing the sun. And lastly, as you notice before, that equatorial ionization anomaly, you have northern and southern crests in the ionization away from your magnetic equator. So that's why what you can notice here is that these ionization crests are actually around 2 plus and minus 200 to 20 to 30 degrees north and south magnetic latitude. And there is a relative decrease in ionization along the equator. Okay. And last variation that I want to talk about is variation in solar and geomagnetic activity. As I mentioned earlier, higher solar activity, we expect higher ionization. Lower solar activity, we have lower ionization. And this is depicted by in this figure. Top panel, global TEC map, average TEC. South, second row, you have your north and south average TEC. And then this is graphed against solar EUV radiance, which basically follows your solar cycle, your 11-year solar cycle. This is solar cycle 23. And then you have geomagnetic activity. So again, as I mentioned before, the more active the sun is, you have higher occurrences of active days, geomagnetic active days, which is basically followed by variation in global TC. Okay. Now you may wonder, how do we measure the ionosphere? Sun, we measure the sun using satellites, SOHO, STO, etc. But when you measure ionosphere, it's a little bit more complicated. That's why that will be our next topic for our next meeting.